Let's do problem 2.5 from Introduction to Quantum Mechanics by David Griffiths. So in today's problems, we have a particle inside the infinite square well with a particular wave function that is given over here, and it has 1, 2, 3, 4, 5 parts up until part E. So without further ado, let's begin with problem number 1. The problem number 1 says that you need to normalize the wave function, basically find what A is. And the rest of the information just tells you that you can exploit the orthonormality of the stationary states, which are psi 1 and psi 2, and this would help you out. So let's begin. So for part A, we need to normalize our wave function, normalize psi. All right. So in order to normalize psi, let's write down the normalization equation, which is taking the integral from 0 to a of psi star with psi dx and set it equal to 1. What this is basically saying is that if you have your infinite square well, you have your infinite square well over here, which has this length of a units, and your particle is trapped inside this box, and the probability of finding your particle inside the box of length a is 100%, is 1. All right, so this when you break down the terms inside the integral, basically becomes the same integral with that kind of looks like this. So you have psi 1 star psi 2 star inside times a psi 1 as a function of x plus psi 2 dx. All right, so if you do further algebra, you could see that you can bring out the a star and a outside, and you have a squared times the integral that has the form psi 1x psi 1 plus psi 1 star psi 2 plus psi 2 star psi 1 plus psi 2 star psi 2 dx. All right. Now, in the next line, what we're going to do is we are going to separate out 4 of these integrals. And if we separate out them, then we have psi 1 star psi 1 dx plus integral of psi 1 star psi 2 dx, 0 to a. Then another integral from 0 to a of psi 2 star psi 1 dx plus the last integral from 0 to a psi 2 star psi 2 dx. Now this is where we are going to use this is where we are going to exploit the orthonormality of the stationary states. Now remember that when you take the integral of let me use a different ink. When you take the integral from any bounds from, let's say here it's 0 to a of psi m psi n dx, all right, this gives you the Kronecker delta function, right? And the Kronecker delta function is 0. This is 0 when m is not equal to n, and 1 when m is equal to n, right? So using this, you could see that this term, the second term, and the third term, they become zeros, right? And all that we are left over here is this and this, and this equals 1, and this also equals 1, using the property of orthonormality of stationary states, orthogonality, I should say. All right. So then we have that this is a squared times 1 plus 0 plus 0 plus 1, and this is equal to a squared times 2. All right, and this entire thing we set it equal to 1, right? So a squared is basically 1 over 2, and therefore the value of a is 1 over square root of 2. And this is how you do part A. Part B basically tells us to find out what psi x comma t is and psi x comma t whole squared is, and later says to express the latter as a sinusoidal function, and to simplify the result in terms of this, omega being equal to pi squared h bar all over 2ma squared. And omega is the angular frequency. Let me write this down. This is angular frequency. All right. So we need to find out what psi x comma t is. This is the time evolution of the total wave function. So recall that psi x of t is a product of your position dependence and your time dependence, all right? And your position dependence of your wave function is a linear combination of all possible states. So we can write down psi x of t as a summation over all n's of psi of x times the time dependent part, which is e to the negative e sub n all over h bar t. All right, so recall that your psi of x is basically a psi 1 plus psi 2, right? Both basically are functions of x, the stationary states inside. So we can write this down as 1 over the square root of 2 psi 1x e to the negative I e1 all over h bar t plus psi 2 x e to the negative I e all over 2 h bar t. And a 1 over square root of 2 is basically your a. All right. In order to find psi x comma t whole squared, what we do is we multiply psi x comma t with its complex conjugate, which is basically the star. All right. And this is basically some tedious algebra, which I'm going to go through with you because quantum mechanics is a lot of tedious algebra. So we plug this in and we get a star psi 1 star e to the I e1 all over h bar t. This is not minus but plus because you're taking the complex conjugate, plus psi 2 star e to the I e2 all over h bar t times a psi 1 e to the negative I e1 all over h bar t plus psi 2 e to the negative I e2 all over h bar t. All right. So basically you have a squared over here. So this becomes a 1 over 2. All right. And if you multiply this with this, the algebra works out to be psi 1 squared plus psi 1 star psi 2 e to the negative I e2 minus e1 all over h bar t plus psi 2 star psi 1 e to the I e2 minus e1 all over h bar t plus psi 2 squared. All right. Now recall that in the infinite square well, the stationary states psi n were written down as the square root of 2 all over a sine n pi x all over a, where n is the energy level where your particle is at. All right, so basically if this is the case, then you can write down that psi n conjugate is basically equal to psi n, right? Because there's no imaginary numbers inside. So taking that into account, we can incorporate that psi 1 star, we can say that psi 1 star and psi 2 star, psi 1 star psi 2 is equal to psi 2 star psi 1, right? So we can do further algebra and we can write this entire term down as psi 1 star plus psi 2 star plus psi 1 psi 2 times e to the negative I e2 minus e1 all over h bar t plus e to the I e2 minus e1 all over h bar t. All right. Now recall this has a form of the Euler equation, right? The Euler formula, which basically says that e to the ix is cosine of x plus I sine of x, right? and e to the negative ix is cosine x minus I sine x. So by doing algebra, you'll be able to find out that e to the ix plus e to the negative ix is 2 cosine of x. And we're going to use that relation over here, and we will get that this has the form of 2 cosine of e to the 2 cosine of e2 minus e1 all over h bar t. And we write this down over here. This has the following form: times 2 cosine of e to the e2 minus e1 all over h bar, and I should write a t inside like this. All right, and we should close the bracket over here, parentheses over here. All right, so now what we're gonna do is we're gonna break down our e2 minus e1 all over h bar. Okay, now recall that in the infinite square well, the allowed energies E sub n had the form of n squared pi squared all over h bar times h bar squared all over 2m a squared, right? So in that case, e2 minus e1 is basically 4 pi squared all over h bar squared minus pi squared h bar squared all over 2m a squared, right? So if you divide this entire term by h bar, right? If you divide it by h bar, the squares cancel out from each of the h bar squares in the numerator, right? And you finally get 3 pi squared h bar squared 2m a squared, right? And if you go and reread the question, this entire term pi squared h bar squared all over 2m a squared is your omega, your angular frequency. So we can write this entire term, 2 cosine of whatever this is, as 2 cosine of 3 omega t. Okay, so we're going to write this down as 1/2 psi 1 squared plus psi 2 squared plus 2 psi 1 psi 2 cosine of 3 omega t. All right. Next up is question number C. Compute the expectation value of x. Notice that it oscillates in time, and then it later asks us to find out what the angular frequency of the oscillation is, as well as the amplitude. It also says if your amplitude is greater than a over 2, go directly to jail. Well, this is a reference to problem 2.4 that we did in our previous video. I will link that video down over here, and that will probably help you. All right, so let's go on to problem C. So basically, we need to find out what the expectation value of x is, and the expectation value can be found out by taking this integral over here of psi star x comma t by sandwiching x in between the conjugates of psi x comma t, psi of x comma t. All right, so by doing further algebra, by expanding each of these terms, you will get that this is a squared psi 1 star e to the I e1 all over h bar t plus psi 2 star e to the I e2 all over h bar t times x times a psi 1 e to the negative I e1 all over h bar t plus psi 2 e to the negative I e2 all over h bar t dx. All right. So again, you can bring these a star times a outside, and that becomes a squared, which is basically 1/2, right? And inside you have a bunch of integrals. So the integrals are those of psi 1 star by multiplying this with this, all right? Plus you have psi 1 star psi 2 e to the negative I e2 minus e1 all over h bar t. That's obtained by multiplying this with this. uh, time plus, oh, I should write this down as this, plus psi 2 star psi 1 e to the I e2 minus e1 all over h bar t, right? Plus psi 2 squared. And you can keep the x outside because the function x is over here. All right. So if we multiply the x with each of these integrals over here, all right, I should write this down like this. So if you multiply x with each of these terms, then you have the integral of 0 to a of psi 1 squared x dx plus the integral of 0 to a of psi 2 squared x dx plus two of these integrals over here. And recall that we said that psi 1 star is equal to psi 1 and psi 2 star is equal to psi 2. So that entire thing makes this whole term over here basically equal to 2 psi 1 psi 2 cosine of 3 omega t. All right, so we have that this is the integral of psi 1 psi 2 cosine of 3 omega t x dx, and the bounds being from 0 to a. I pulled out the 2 outside from the integral because that's basically a constant. All right, now notice that this is basically the expectation value of x when n is equal to 1. And this is the expectation value of x when n is equal to 2 and n is equal to 1. All right, so in problem 2.4, and I will link it in the description below, we found out the expectation value of x in the infinite square well, no matter what, is a over 2. So we can write this down as a over 2 plus a over 2. Yes, so this is a over 2 and this is a over 2. All right, so we are left with the last integral over here. So what we're going to do is we're going to break down psi 1 and psi 2. All right, so you have psi 1 is equal to square root of 2 all over a sine pi x all over a. This is the first stationary state with n is equal to 1. Then we have the square root of 2 all over a sine 2 pi x all over a. All right, and we have an x with a cosine of 3 omega t dx. And if you do further algebra on this, you will have that this is 1/2 plus a plus, if you bring out the constants outside, you have 2 times the square root of 2 times the square root of 2 all over the square root of 1 times the square root, the square root of a times the square root of a cosine of 3 omega t times the integral from 0 to a of sine of pi x all over a times sine of 2 pi x all over a x dx. All right, and this integral over here is very tedious to do. So I'm just going to write down the result of this, and you can find this in Wolfram Alpha or integral calculator, whatever software you'd like to use. But this is negative 8a squared all over 9 pi squared. Trust me on this. So the final result basically becomes a plus 4 all over a cosine of 3 omega t times minus 8a squared all over 9 pi squared. All right, and if you do more algebra, you get this. This is basically a minus 32a all over 9 pi squared cosine of 3 omega t. And you can, of course, pull out the a from within the parentheses, and you will get that this is a all over 2, 1 minus 32 9 pi all over 9 pi squared times the cosine of 3 omega t. And this is your expectation value of x. Now, as for the amplitude, The amplitude is basically a all over 2, 32 all over 9 pi squared. And this is achieved by comparing this equation with that of the wave, which is x is equal to a cosine of omega t. All right. And as for the angular frequency, the angular frequency is visibly 3 omega. 3 omega, and you can break this down and write this down as 3 pi squared h bar squared all over 2m a squared. Let's do part D right now. Part D is basically computing what the expectation value of P is. And this can be achieved using a very clever trick. So if we want to compute the expectation value of P, you can either take the integral of psi x and sandwich P, the operator P, in between these. And this is very tedious. In our case, it's easier because since you know what x is, the expectation value of x is, since we know this, we can write the expectation value of P in terms of momentum, which is m d dt x, and find the expectation value of this. All right, so the expectation value of P is basically the expectation value of m d dt of x, right? And since m of the particle is constant, we can bring it outside, and we have that this is the first derivative, m times the first derivative of the expectation value of x, right? So by doing further algebra, we get that this is m d dt of the expectation value of x, and the expectation value of x is a all over 2, 1 minus 32 all over 9 pi squared cosine of 3 omega t, right? And you can of course bring the a all over 2 outside since this is a constant, and you have ma all over 2 times the derivative of the term that is inside. All right, and the derivative of the term that is inside is 32 all over 9 pi squared sine 3 omega t times 3 omega, and you can of course simplify it, and this approximately becomes 96 ma sine 3 omega t all over 18 pi squared. And lastly, the last problem tells us that if you measure the energy of this particle, what values might you get, and what is the probability of getting each of them? And lastly, it tells us also to find the expectation value of h, which is the Hamiltonian. All right. So since we know that our wave function, which is psi, is a psi 1 x plus a psi 2x, we know for sure that it has energies E1 and E2, right? Because the stationary states are those of n is equal to 1 and n is equal to 2. So we write down that measuring the energy would give energies E1, which is equal to pi squared h bar squared all over 2 ma squared, and E2 being pi squared h bar squared times 4 all over 2m a squared. And their respective probabilities are its coefficients but squared, right? And so the probability of measuring each of them is a squared, right? And we know that a is equal to 1 over the square root of 2, which we found out previously, and this is basically 1/2. And then again, we have to find out what the expectation value of the Hamiltonian is, And the expectation value of the Hamiltonian is basically the sum of all Cn squared E sub n, where Cn are the coefficients of your stationary states in the expansion of your total wave function, right? So in our case, the Cn's are basically your A's, all right? So you have A squared E1 plus A squared E2. And since A squared is 1/2 and E1 is pi squared h bar squared all over 2ma squared, you have this term that looks like this. And you can further simplify it if you want to, but I like to keep it like this because I don't want to do further algebra. But here we go. This is solving problem 2.5, which is very tedious, of Introduction to Quantum Mechanics, Chapter 2, written by David Griffiths. That's all.